All right, ladies and gentlemen. So we have finished our cheat sheet for our AP test, which means we kind of have a general outline of what we're gonna do for all the different problems. So one of the big not criticisms, because you guys would never criticize anything I do. Just kidding. One of the big sticking points, I guess, that I've gotten from you guys as far as I'm confused about the AP test. How do I do physics? Is we're confused on how to tell when to use what formulas and stuff. So we're gonna spend some time today talking about the big three, which are forces, momentum, and then work or energy. We're gonna try and figure out how can I figure out when to use these. These are about 50% of the test, maybe a little more, maybe a little less. But I guarantee there's going to be at least one question that talks about these things on the test. It might even be a combination, which we'll see in a second. But we need to kind of be able to look at a problem, figure out what information they're giving us, and then at least have a guess to which one of these I want to try. Because it is a time test. It's only 45 minutes, so we can't try something for half an hour and go, oh, wait, that's not going to work. Just kidding. We kind of want to guess it right the first time or the second time. So let's start by looking at the formulas for these three different topics and kind of just get acquainted with them, get familiar with what they do and why we want to use them. So for forces, okay, of course we have all of our regular force equations, right? We have the force for springs is negative kx, and the negative again is just saying whichever way you stretch it, it pulls the opposite direction. We have gravity, right? Force of gravity or weight is mg, stuff like that, right? The big idea, the big thing you're going to use for forces in almost every single problem or scenario, right? These are specific forces. Those aren't important. You can look those up. The big idea for solving force problems is that the sum of forces, so this could be weight minus normal force minus force applied equals, and then it's either going to equal 0, that would be balanced, or our sum of forces will equal ma. This is unbalanced. And then there's one more that it could equal. It's mv squared over r. This is uniform circular motion. Okay, that means something's spinning in a circle at a constant speed. These are the big tools you're using for forces, right? So anytime you're going to do a forces quote unquote problem, right, and you're going to use forces to solve the problem, what you're looking for is, can I set up this sum of forces equation? You have to be able to figure out what are all these forces, or what are all the equations, and then you have to know what to set them equal to, and then you have to be able to solve those. Okay, so for forces, we're looking, do I know most of the forces or all of the forces, right? We'll also talk about something else that kind of is a hint for forces. Okay, let's look at momentum. Momentum's not quite as cumbersome because there's only 2 equations for momentum. So for momentum, whoops, my pen's, come on, pen. Okay. Sorry, I haven't written with it in a day or two. It's getting all dried out. Okay, momentum. There are only really 2 equations here. We have momentum is mass times velocity, okay, and then we have impulse, which is the change in momentum. The variable is j. It is a vector. Is either, you can sometimes use mass times change in velocity. This is kind of handy if you know the mass and you know how much it's sped up or slowed down. You can use that to find your impulse. There is a fancy formula for impulse, though. It is force times time. These are really the only two options you have for momentum. So you either have to know some momentums or you have to figure out what is the change in momentum. So the first thing you're asking is the momentum conserved? So P initial equals P final? Or did our momentum change? Change in momentum is impulse, force times time, or mass times change in velocity. These are the only two types of momentum problems that exist. Either momentum is constant or it's not, right? So these are the two things you're trying to set up. So the thing you are going to really focus on for momentum problems is either that, the change in velocity. You're going to go, oh, do I know some velocities? I know how fast it is going at the start. I know how fast it is going at the end. I know some stuff like that. That might be a momentum problem. If it's a collision only has one. Collision, right? It's a word, English. If there are collisions, it is a momentum problem. So you say this thing is coming in here. I should draw, right? This thing is going that way. It hits this thing. Now they are like a bigger block, and it's going that way together, right? A collision would definitely be momentum. Anytime two things bump together, it's really hard to describe the forces going on there. So we go, you know what? This is too hard for us. We're going to use momentum. Okay. This is also your average force technically for this class, but it's nitpicking. Okay. Last thing we want to talk about is energy or work. Okay, so our equations for energy. Energy initial equals energy final. Whoa, it's very similar to momentum. Don't get lost. Okay, or if energy changes, then there was work, and that's force times distance that's an S, cosine theta. Well, look, change in momentum, change in energy. Conserve momentum, conserve energy. These are very similar. Okay, so let's talk about this. Work and energy. Energy, we have a couple different types. We have kinetic energy. We actually have two different types. We have V squared. This is for translational, things going in straight lines. Okay. We also have kinetic energy rotational, which is 1/2 I omega squared. That's for things spinning, right? Then we have gravitational potential energy, which is mgh, for stuff close to the Earth's surface. And then we have gravitational elastic, which is 1/2 kx squared. K is our spring constant. It's how stretchy something is. Bigger K means less stretchy. It's really stiff and hard to stretch. Small k means really stretchy. And then x is how far you stretch it. Okay. So your goal for work and energy is either conserve energy. So I start with some kinetic energy and then the ball goes up, so it gains potential energy gravitational and loses speed. So my energy is UG, do that. Or if you say something like, well, my box is sitting here at rest. I'm going to push it 20 meters. How fast is it going now? Well, it was at rest, so it had no energy. Now it's going fast, so it has kinetic energy. So we changed the amount of energy we have. We did work. So we have to know the force and the distance. Okay. So now let's maybe talk about what variables we'll see in the different problems, and then we will try and figure out what we should use to solve them. Okay. So forces, we're looking for, do I know all the forces, right? Or am I trying to solve for a piece of the forces? Can I set up a sum of forces equation? Momentum, you want to know initial and final velocities. We want to be looking for how fast is stuff going, or we want to look for, did a collision happen? Are two things bumping into each other? That's probably momentum. And then work and energy is for when forces don't work. If I don't know all these forces, or I have weird forces I don't understand very well, say a collision, two things bump into each other, I can't use forces because I don't know how to describe that force while they're bumping. So that's not good, right? So I can't use forces. I don't understand the forces well enough. Energy is typically used for if things are falling, if things are stretching a spring, or things like that. It's converting from saved up energy, springs or things lifted, and converting it into speed, making things go fast. Okay, so that can be similar to momentum, but this is more like if we know the beginning and the end positions. This is more positional. It's where am I? Then I can tell you information about what's happening at that location. This is more like how fast am I going? Okay, and we'll look at some of these. Okay, all right. So what you guys are going to do for homework, I'm going to post this so that you guys have them. But what you're going to do for homework is you're going to solve these 4 problems. What I'm going to do with you guys in the rest of this video is I'm going to help you come up with an idea for these 3. Which one are you going to use? And I might help you set up the problem, and then you need to finish these 4 and then send me your work. Okay, and you guys can, if you don't want to write these all out, you can number them 1, 2, 3, and 4, or you can print them and then just write on them or something. But I'll post them so you guys can print them if you want. But you need to do these 4 problems. Like, you need to solve for the variable it's asking for and give me a number. Okay. All right. So it says for number 1. A 10 kilogram mass is being pushed along a rough surface and is accelerating at 1 meter per second squared. Find the coefficient of there should be an of right there. I'll fix that. Find the coefficient of kinetic friction between the surface and the mass. Okay, so we're not looking at 2, 3, 4. Let's go through, maybe look and see what information did they give us, and then we'll try and figure out which one of these approaches we want to take. So, all right, they give me a mass of an object, which is important. We have a rough surface. That means there's probably some friction. And I have an acceleration. A equals 1. And we're looking for the coefficient of kinetic friction. That's mu. Okay. So now I need to pick some of these. Because we're talking about friction, we are looking for a part of a force. We're going to be solving for a force or a chunk of the force. We need to know information about the forces is kind of what I'm getting at, right? So immediately you should be thinking, oh, forces. But let's talk about why energy and momentum are a bad idea. Okay. So we have this thing being pushed along a rough surface and it's accelerating. Do you see acceleration anywhere in any of these equations? Let's see, mass, velocity, mass. That's a no. No, there is no acceleration. So what am I going to do with this information, right? Like, why do I have this? It might be extra. The AP test does that. But that's one of 2 numbers they give me. It might be important. I'm also looking for a force. It's probably, you know what, you guys, I might be dumb. We'll talk about that. Okay. So we have this mass. We have all this, yeah. Okay. So no accelerations here, no accelerations here. We can't use the acceleration. If I'm trying to solve for force, friction equals mu times our normal force. It has to be forces, right? We're not looking for velocity. It's not even a constant velocity, and there's nothing that the thing is colliding with. And it doesn't say that the rough surface starts to move, so it's not like our mass is transferring some momentum to the rough surface. And we don't know the force or how long it's pushing, so we can't use impulse either. So we have a bunch of formulas here and not a lot of stuff to plug into them. So for this problem, what we want to do is forces. So we're going to try and write a sum of forces equation, right? So our sum of forces Oh, I have to do some forces. I should probably figure out my forces. Let's draw a force diagram just like we had on on our cheat sheet, right? Oh, I need to draw a force diagram and solve for it. Write a sum of forces. It says it's accelerating, so it's going to be equal to 1. Once you fill out these forces, you should probably go ahead and try and solve for a variable, or maybe make some substitutions with your equations. Okay? So we are saying this one has to be forces because we have an accelerating system. There's no accelerations here for us to plug into. There are no accelerations here. We don't have any collisions, so it's not momentum. And we don't know a lot of information about the beginning and the end of the problem. We don't know how fast it was going. We don't know how fast it ends up at. We don't know how far it goes. So we don't have any velocities. We don't have any displacements. We don't have any height changes. Energy is pretty worthless to us. The only thing we might want is this force, but we don't know what our starting energy or final energy is. We don't know the force. We don't know how far it went. There's too much missing information for us to use. Forces, we do know the forces acting on the object. We've got some weight. We've got some friction. We've probably got an applied force pushing the box so that it's opposing friction, things like that. Okay, so we know a lot about the forces. We have an acceleration. We're looking for force information. We should go with the forces route. All right, let's look at number 2. A 10 kilogram mass is being pushed along the rough surface and is slowing down at a rate of 1 meter per second squared. How far will the box travel before coming to rest if it was initially traveling at 5 meters per second? Okay. So this question is sort of a trick question because I think there are 2 ways you could solve this. And it's kind of because I gave you this acceleration, this velocity. If I'm going 5 meters per second and I'm slowing down 1 meter per second, how many seconds is it going to take to stop? Think about it. You're going to go, oh, Barton, that's tricky. Oh my gosh, that's so crazy. When will velocity get to 0? If it starts at 5 and I take 1 away after 5 seconds. Okay. So because you kind of know t equals 5 seconds here, you could probably just use your velocity, your acceleration, and just say, well, they didn't tell me where it starts, so x naught equals 0. And use a distance equation for this. X final, how far, equals x initial plus initial velocity times t plus 1/2 at squared. And you could plug it into that equation. So it's not really a forces, momentum, or work equation either way. Because I give you so much information that we can just plug into here, right? If I don't tell you this acceleration, if I maybe made you go find it, if I gave you this problem, and instead of giving you the acceleration, I maybe give you the coefficient so you can find the acceleration, then this has to be a combination of forces and maybe work. If I just gave you a force, let's say friction is 1 Newton, right? Then this is definitely a work problem because we are going 5 meters per second. So we have kinetic energy to begin with. It's going to come to rest. We're going to lose all of our energy. So my energy is going from whatever 5 meters per second for a 5 kilogram box is, or a 10 kilogram box, to 0. So we're doing work. We're taking energy out of the system. So if I know the force and I know how much energy we lost, we can solve for x. Yeah? Okay. So, yeah, go ahead. This one will be work. The reason we know it's work is because we can kind of know the force. We know we could figure out the change in energy really easy. Again, there's not a collision, so we're not doing momentum. And the forces, we could maybe use forces on this. You could probably use this. But if you do, you're going to go back to using the position equation. So I would go the energy route, right? Change in energy think about what type of energy I have. Energy initial, no, energy final minus energy initial. You should fill out what types of energies those are. Equals force. Let's see, you know the acceleration, you know the mass. Force equals mass times acceleration times distance, and you're trying to solve for that distance. Okay. Number 3, it says a 10 kilogram mass still is being pushed across a rough surface, and the coefficient of kinetic friction is now 0.6. That's not the answer to number 1. I made this number up. Don't use 0.6. How far will the box travel before it comes to rest if it's initially traveling at 5 meters per second squared? So this is what I was talking about with this. I put this here to kind of show you why you can't use this anymore. We don't know the acceleration, so we can't plug that in. If I'm going 5 meters per second and I don't know the acceleration, how long does it take to stop? We don't know time anymore as easily. So you can either find time and acceleration and then use this distance formula. That'll work here, but I think that's the hard way. You should use the energy like I was saying. Our starting energy is kinetic because it's moving. Our final is 0, so minus nothing, equals force times distance. Okay, our force is friction, which is mu times our normal force. So K equals mu, N times X. You know mu, you can figure out N really easy because it's just a box on a flat thing. And then, work. Okay. Number 4, a girl is skating with her friend. She sets down her board and gets a running start to jump on it. The skateboard is initially at rest. Velocity starts at 0. Okay. While the girl is running at the skateboard at 1.5 meters per second squared. This problem has 2 different bodies, 2 different masses with 2 different velocities. We have the skateboard and we have the girl. Anytime you have 2 different things with 2 different velocities, they're probably either going to collide or explode. This is momentum, right? If they start describing multiple things moving with different velocities and then they interact with each other somehow, they pull on each other with a string, they are attached by a spring, they have friction, they touch each other, they run into each other, any of that is probably momentum. So a girl has a mass of 47 kilograms. The board has a mass of 1.5 kilograms. How fast is the girl going after she lands on the skateboard? So we're looking for the final. Okay. This is momentum because they're telling us velocity, mass, velocity, mass, velocity, right? Mass, velocity, mass, velocity. The equation for momentum is mass times velocity. They're telling us to use our momentum here. Okay. So for this one, you want to ask yourself, is your system open or closed? So you say, all right, are there outside forces? Well, they didn't tell us anything about friction. I'm going to say my system is the lady and her skateboard. Okay. So if I'm just looking at the girl and a skateboard, this is a closed system because the only things we're caring about are the girl and the skateboard, and there's no friction, there's no air resistance, there's no ball, there's no applied force, there's nothing outside the system touching anything inside the system besides the normal force on the skateboard from the ground, but it's not going to make it fly up. It's balanced, so it doesn't really matter. Okay, so we want to say momentum initial equals momentum final. So initially, what's moving? Is the skateboard moving? Is the girl moving? So it should be momentum of the skateboard plus the momentum of the girl, both of them initial, equals the momentum of the skateboard plus the momentum of the girl, final. And then you should be able to substitute these for a bunch of MVs and plug in most of them. Remember, these two are moving together. The girl is going to be on the skateboard. So when you say the final one here, you're going to want to stick their masses together. Mass of the girl plus the mass of the board, and just do times a single final velocity, because this final velocity is that thing's final velocity and that thing's final velocity. They're shared. It's the same number. So if you distribute this like you do in algebra, this is the mass of the girl. Sorry, mass girl v final. So her final velocity plus mass board v final time plus its final momentum. Sorry. You guys, it's hard to teach, I'll tell you what. Okay, so initial momentum equals final momentum. And we know it's momentum because we have two bodies interacting with each other, and we have a bunch of masses and velocities. So that's kind of the tip there. Okay, so there are your notes. You are going to do these 4 problems. I've already set them up pretty much for you. You're going to do them. Either take a picture of them, type them, I don't really care. Send them to me via a picture on either Band or Google Classroom, and then I will give you points for the week. All right, enjoy.